Hello everyone, thank you for tuning into this presentation on the development of the digital twin of a Lego helicopter. I am Karel du Plessis and I will be taking you through this process. Just a brief look at the agenda. I will give you a quick run through of the background to this story of the Lego helicopter and its developments. I'll introduce you to the team and we'll ask the question on how to develop this digital twin and see how that plays out on the specific example of the Lego ultralight helicopter. So why did we choose this Lego helicopter? Well, in the first place, to demonstrate the use of the entire suite of software contained within Simcenter, and that will entail the use of Teamcenter, NX for the computer-aided design and computer-aided manufacturing parts, the CFD part, which will be done with Simcenter Flow EFD, the structural analysis, the motion analysis, and the systems and control being conducted within the Simcenter AIM-Sim suite of software, coupled to the multi-body dynamics analysis, as well as looking at the plant design of the manufacturing on the digital manufacturing side. So why a Lego helicopter? Well, because everybody loves Lego, especially us engineers and the wider community. And obviously we don't have actual helicopter assembly models lying around, so then what else are you left to do? But more than that, the purpose of this presentation or this project was really to demonstrate the use of complex CAD geometry, in the sense that the geometry, these various components may be very complex, even though the actual assembly isn't all that complicated. But in terms of CFD specifically, that was the main aim. So just to introduce you to the team, we have J.R. Delapierre on the Teamcenter and requirements task planning side. We have Armand du Plessis and Hermes Hendrikse on Technomatics, looking at the plant design and manufacturing process planning. And then the mechanical engineers that you will see on the right there, which will be Rowan van der Merwe on the Simcenter motion and NX CAM side, Andrew Barrett with the structural analysis, and myself looking at the Flow EFD and AIM-Sim software. So, what is this digital twin? Is it just simply a computer model, a CAD model of an assembly, or is it something more? Well, yes. It is definitely something more. The digital twin is really about engineering innovation. It is supposed to include simulation as an upfront in the design stage of the product development. So that will include CFD, FEA, CAM, motion, systems control, manufacturing, all of the different engineering related processes on a digital model, a digital twin, if you will, of the actual real world model or product, so that everything can be virtually tested and developed before any prototyping can occur. And this will require a collaboration between multiple disciplines, teams, and skills, as well as an integrated and unified environment, which will allow multidisciplinary design and simulation to be conducted. And it will also need to include data management, which makes sure that all of the data and the models being used by the diverse team and disciplines will be centralized and synchronized so that everybody works from the same model and the most recent version of that model. And all of that will happen within the Simcenter suite of software and the wider Teamcenter collaborative environment or platform. So just a quick run through on the workflow. You will see there that we will be going through different stages on the design side, as well as the simulation, and then finally the manufacturing side. And all of that will be controlled by the Teamcenter environment, maintaining strict control on revision process and requirements to be met. And then you will also then see the Simcenter suite of software will include the design, performance engineering, and the machining part, whereas Technomatics will be looking at the manufacturing and production and plant design. Okay, so getting on with it, so having a look at how the requirements are conducted within Teamcenter. Here you can just see a quick video of how the requirements will be set up. For instance, looking at the documentation that needs to be drawn in and updated and maintained. See here a video of how the documents, and so forth can be imported. And just to look at what those requirements entail for the specific project. Obviously, making a Lego helicopter fly isn't always that easy, so we have just had to come up with a bunch of requirements that we could physically achieve. And these are then the requirements that we were looking at while we were doing the design and simulation of the Lego helicopter. So getting on to the design within the NX environment on the computer-aided design side. NX basically is a very powerful CAD environment with a lot of design freedom and endless capabilities, but it really forms the backbone to having a centralized and controlled CAD model to ensure a fully integrated development platform for a digital twin, which is actually one of the key aspects. And it ensures access to most up-to-date version of the design. It's a quick and seamless update of the downstream simulations because everybody works on the same model. The same CAD model is used for CFD, FEA, multi-body dynamics, and the like. And there is no translation with the loss of data being a problem when transferring information from one environment to the next. And then moving on to performance engineering. So once we've established the CAD model, one can start looking at the simulations, and here you'll have the breakdown of the flow. You'll see when we move from the CAD environment, the CFD environment is the first aspect and actually one of the most important ones to get right. So CFD will be first in the process to analyze, for instance, the lift that can be generated by the rotor blades and also some of the other rotor equipment providing the thrust. But then moving on from there, you will see the downstream processes all relying on the CFD part being conducted first. Right, so let's consider the original rotor blade, which was referred to as revision A. Here you can see within Teamcenter, everything being loaded into a controlled environment. One can open up NX from within Teamcenter, load the model from there, and you will see the Flow EFD setup of just the main rotor assembly in order to have a look at the lift and drag, or then the required torque for that specific angular velocity. Okay, so once we've seen that we cannot generate the lift that is required, we will have to go through a design revision. And what you will see there is that within Teamcenter, a new revision of the rotor blade is created, and that parameterized airfoil can then be used within the subsequent designs. But being an integrated environment and working on a unified CAD model, you will see that the FlowEFD simulation has already been set up, so it's very quick and easy to just conduct the next simulation. Here you can see, based on some assumed airfoil shape, we are already showing some reasonable improvement on the lift, but we are still not meeting the requirements, so the CFD requirement has not been met, and we will have to go through another revision, which is very easy to do. So because the model is parameterized, we can set up a optimization study on finding the correct blade or airfoil shape that will provide sufficient lift while maintaining the right drag coefficient to prevent the rotational torque to be exceeded. So here you can see a quick setup of the HEATS multi-parameter optimization embedded within FlowEFD. And once we've gone through that study, you can see there's a bunch of feasible designs that were populated, and one can choose from the range that was generated which one generates the highest lift to drag ratio, which in this case was the optimization goal. So knowing that, knowing the parameters that will give us the best lift to drag ratio, we can then go through a revision on the CAD model using those parameters. Go through that revision. It's now going to be revision C. And you can see, because we are now exceeding the limits of the envelope for the rotational diameter of the rotor blade, one can just update any component, and the component will be revised within Teamcenter, and we will see that even that connection will be updated to be a revision B. So once we've done that update, you could see that we are now very effectively meeting our requirement on the lift as well as the rotor blade torque, and from there on we can move on to the FEA analysis. What you can see here is the pressure distribution on the blade being exported to the text files that will be imported by the FEA simulation engineer, who gets the model from Teamcenter. And here you can just see a quick run through of the setup of the finite element analysis, where you will see the file being imported from the pressure distribution and mapped across to the finite element model as a new field, picking up the file that was exported from FlowEFD and applying that as a pressure distribution field. Seeing there the mapping happening effectively and the resulting deflection because of that. However, with that specific blade design, we are exceeding the requirement of a maximum of 3 millimeters lift, and therefore the design will be revised. But we sit with a problem that all of the high lift to drag ratio airfoils will suffer the same fate because they are all effectively very thin. So the only other option one would have is to look at some of the thicker airfoils which produce a reasonably high lift to drag ratio, and to see how they compare on the lift that is required. So quickly opening up the rotor blade model again, updating it with the parameters for the next most feasible option, and quickly running the flow FD simulation again, reveals that yes, we are effectively passing the requirement. And what you also see is that even though the lift is a little bit lower, the total required torque will also be a little bit lower because we have lower drag as well. So the CFD requirement is passed, and redoing the finite element analysis will reveal that yes, the thicker profile is very effective in meeting the requirement on the blade tip deflection. So that is a pass, and we can move on to the computer-aided manufacturing aspects, which we quickly run through here, where the computer-aided manufacturing process is demonstrated here as having a bit of a problem to cut the leading edge because it has a fairly sharp leading edge. But this is not to say that NX cannot do this, that we forced it to cut through the leading edge like that, to force it to fail, just to demonstrate the process of going through another revision on the computer-aided manufacturing side as well. Okay, but that would require having to go all the way back to revising the CAD, the rotor blade, and conducting the CFD analysis again. So here you can see making the leading edge a little bit more round will result in pretty much the same lift being generated, but a slight increase in the torque required to rotate the blade due to the slightly more rounded leading edge, but sufficient enough to pass the requirement and move on to the FEA analysis. We do know that the FEA will not be a problem because it's effectively the same thickness, it's just the leading edge that was a little bit more round. So just quickly running through the same process of simulating the manufacturing or the machining of this new blade will show that yes, it will indeed pass. So once we've got that done, you can now move on to the multi-body dynamics analysis, where it was actually required to incorporate the lift being generated by the rotor blade for different blade pitch angles, as well as different speeds for the tail rotor as well, which also goes through a revision because the initial design was not sufficient. And an update to that will demonstrate that the thrust that needs to be generated is possible. We also need to characterize the entire helicopter for its aerodynamic characterization. So having to characterize the drag versus airspeed is also done, so that we have these characteristics that we can then incorporate into our multi-body dynamics analysis, which will run in conjunction with the control system that is developed within AIMSIM. So here you can see just the control block that connects AIMSIM with the motion space within Simcenter, with all the characteristics that we just simulated for the helicopter lift and drag characterization. Okay, here you can see the setup of the multi-body dynamics analysis of the helicopter, with a flex body on the suspension component there. And just to demonstrate the result of that, the blade pitch being controlled with AimSim. You can see the blade angle being increased to generate the lift required to take off, and then the rear prop also starting to rotate to maintain a vertical ascent and then to move forward and eventually descend back down. So within AimSim, one can then conduct the optimization of the system response, the control system response, based on the predefined input of the flight envelope. So here you can see an example of a poor system response. And afterwards, after tweaking the control parameters, you can see there the system response following the flight profile very accurately. And that will then be regarded as a pass, and then we can move on to the digital manufacturing space. So here you can just see how the process planning occurs within Teamcenter, looking at sequencing and planning of production and so forth, using timing, Gantt charts for timing, and testing alternatives for production lines versus job shop, and seeing how they compare in terms of key performance indexes. Then moving on to the assembly line, comparing what needs to be done in terms of updating the assembly line to accommodate the changes we've made to the blade design. So you can see Rev A, the original design, the assembly line that was developed for that works very well. There's no buildup of components on the conveyor belts for its between the assembly points, whereas you could see they're really running on the limits of what the production line can do when you have a single assembly point. Okay, so the throughput per shift can be seen, the difference between the two, where you're occupying pretty much the entire belt with the latest revision. So then looking at different assembly designs where you can either have one additional worker on the same station, or maybe split up the line to have two lines, one for each additional worker, or you can then replace both of them with a robot, for instance, and one can see then the comparison between the three options. All right, so once that is done, one can also have a 3D layout of your assembly line and see how these models get transferred and assembled, and you can also then see any hold up and any potential blocks in the entire assembly line.